Very good. Welcome to ICANX. It's my pleasure to host our talk today. I'm Paul Weiss from UCLA and also editor of ACS Nano. We have a terrific talk for you today, a return engagement of Yury Gogotsi. This will wrap up our July series. Welcome, everyone. So let me first start off by introducing Professor Yury Gogotsi, and I'll introduce our panelists after the talk. Yury is a distinguished university professor and the Charles T. and Ruth M. Bach Professor of Materials Science and Engineering at Drexel University. He also serves as the director of the A.J. Drexel Nanomaterials Institute. He's received a very large number of awards for his research, including a Friendship Award from China, the European Carbon Association Award, the SME Award from the International Union of Materials Research Societies, the Fred Cavalier Distinguished Lectureship in Nanotechnology from the MRS, and the Russ Nano Prize. He's a fellow of the European Academy of Sciences, the American Association for the Advancement of Science, the Materials Research Society, the American Ceramics Society, the Electrochemical Society, the Royal Society of Chemistry, the International Society of Electrochemistry, and he's an academician of the World Academy of Ceramics. He's also a great friend and an associate editor with us at ACS Nano. He's been the pioneer and champion of MXenes, which we're going to hear about today. And it's my absolute pleasure to turn the floor over to Professor Yury Gogotsi. Yury, you're on.
Paul, thank you very much for your kind introduction. Alice, thank you very much for inviting me to speak. And I'm really delighted to be here today. And it's a special honor to speak actually in this very prominent and very prestigious series for the second time. More than a year ago, together with Professor Paul Weiss, in May 2020, I gave a talk introducing actually MXenes, but so much has changed in the field. The development has been so fast that lots of new things happen in this really explosively growing family of materials, two-dimensional carbides and nitrides that you can see in this image in the cover slide. And I am going to talk to you today about progress over past decade in the field of two-dimensional carbides and nitrides, their place in the large family of two-dimensional materials, and also the most recent developments and challenges we are facing here. So it will all be about 2D materials, very thin materials that finds lots of different applications. And if you want to read more about this class of materials, this very recent review will provide more detailed information and a good introduction to the field. But let me first take a step back and talk about two-dimensional materials in general. You don't need to be an expert in 2D materials or even material science to know about graphene. Discovery of very interesting physical properties in single layer and few layer carbon sheets graphene by Andrew Geim and Kostya Novoselov attracted interest to other atomically thin materials with 1, 2, 3, few more atoms in thickness, but large lateral dimensions. They appeared to have many interesting properties. The electronic properties range from metals to semi-metals, semiconductors, insulators. They're atomically thin, and it means they are flexible and transparent. And this is a critical set of properties for advanced technology. We all want to have electronics which is flexible, variable, miniaturized, and often we talk about transparent devices on walls, on windows, elsewhere here. And of course, also, they have very large surfaces open to adsorption, energy storage, catalysis, many other applications. So this family of materials include old materials like clays or moly disulfide, other transition metal dichalcogenides, but also newly produced materials like phosphorine. And interestingly, even materials which have not been known to exist in a layered form, like silicon, germanium, tin, were separated and made into two-dimensional sheets. And among those newly produced materials are carbides and nitrides of transition metals that I'm going to discuss today here. And very interesting, this discovery made about a decade ago led to really like an opening an enormous field of materials science. Materials with really extreme properties not available in other classes materials, but it also to a certain extent plays a closing game for the 2D materials family, because with many semiconducting and insulating materials or semi-metals, remember, even graphene being praised for its conductivity is a zero band gap semiconductor, not truly metal. We added now a very large family of really metallic materials with a high density of state at the Fermi level, with high concentration of carriers to the 2D field here. And really, it leads to a paradigm change. Paradigm change in the field of usage of materials. You hear often about graphene being a wonder material that can solve all the problem. No materials really can. But now having all the building blocks, all the Lego blocks that people can use for making structures and assemblies and entire devices that cannot be made by using any single materials. So we basically move from a single wonder material use, whether it was initially stone and after that bronze, and after that steel, and after that polymers and silicon and graphene, to having thousands of atomically thin small blocks to build. Play with this here. And actually, these assemblies don't necessarily need to include just 2D materials. It's possible to assemble two-dimensional materials with 0D and 1D materials in complex architectures and build materials and devices of the future here. And this is how I see us moving beyond just graphene to many other 2D materials and also assembling them with others. Because in reality, for majority of applications we are considering for future technologies, we need all possible kinds of materials here. We need to combine different materials. For example, materials with conductivity, redoxability used in energy storage, like lithium-ion and other batteries. Conductivity plus catalytic ability gives electrocatalysis. Conductivity transparencies, transparent conductors, electron conductors. Combined with the color, we get optical, electrochromic, photonic, plasmonic devices here. But really materials with high electric conductivity were largely missing from the palette of 2D materials here. And if we have them, we can build a variety of devices. We can assemble 2D blocks. And keep in mind, when you have a 2D structures, it's much easier to assemble them, pile them up, or make a 3D architecture compared to 0D or 1D materials alone here. And after this long introduction, let me actually move to the main subject of my presentation today, MXenes, and explain you what these materials are, why they are unique. What you see here is actually the first structure discovered by Michael Naguib, who was a PhD student working with my colleague Michel Barzoum and myself at Drexel University when it was produced at the end of 2020 and published in Advanced Materials in 2011. What you see here are these golden spheres are actually metal atoms, titanium. Those layers are few atoms thick, just like other 2D materials here. The black one, actually, titanium is metal, M. The black one stands for X, in this case is carbon. And I'm showing it OH termination. Terminate. What is unusual in this material? It has a conductive carbide core. So electrons, free electrons of titanium metal give metallic conductivity to this material. But at the same time, the surface of MXene is usually terminated by oxygen, OH, fluorine, halogens. So it has like a transition metal oxide or hydroxide-like surface. So these materials combine or can at least combine intrinsically properties of two classes materials. You can consider them to be like a conducting clay or ceramic oxide, or you can look at them as, for example, water-soluble metal, because these functionalities provide hydrophilicity, solubility to this material. Moreover, they come in several different groups with different number of layers in the structure. We can make a variety of them, and actually Michael, when he was a PhD student, produced like a dozen of different compositions. Moreover, it's possible to produce solid solution, mix different transition metal, or mix carbon and nitrogen. As a result, the number of compositions can be produced is very, very large. Titanium-32 was the first one discovered here, but discovery continues. I also want to tell you that publishing the work, whenever you have something really new, is not necessarily easy. And as we are celebrating the first decade of research in this field, and the first MXenes were published in Advanced Material, so this is the cover of the journal. This first paper reporting on this new wonderful family of materials was not easy to push through. A couple of journals rejected it without a review, with basically comments like, we already have many two-dimensional material, why do we need more? What is exciting about it here? Dr. Lorna Stimson, who was an editor of Advanced Material at the time, agreed to send it for review. And we got a set of 3 lukewarm reviews telling, well, yeah, that something seems to be new, but what are the properties? What's going on? Will it be useful? And the paper was rejected again. Publishing a paper like the Nature report by Croto and Smalley, where the only real illustration of material is a soccer ball on Texas grass representing fullerene, and speculation about possibility of spherical molecule, is not going to work nowadays. Luckily, Lorna agreed to send it for adjudication review. And I just learned earlier this year, after asking Advanced Materials, that Vincent Munier from RPI was that person who wrote that this is important result, and successful isolation of new 2D crystal by itself should warrant publication in a prestigious journal like Advanced Materials. So this is just a lesson to everyone, young researchers especially, who get discouraged when their work gets rejected, not published, not even reviewed by a journal here. If you have an important work, just pursue your research. You will get it published, and if it's important, it will get recognition here. In 2018, we had the first international conference on MXene in Changchun with about 200 attendees. The number of attendees more than doubled in a conference organized by Bin Shu in Beijing in 2019. There was a search conference during the COVID time organized by Qin Huang in Ningbo. And we also had a virtual conference in 2020, last August, with already more than 2,000 participants. The field is growing very quickly. It's really a shaped field now of MXene research with several thousands of papers already here. Now, it's wonderful to have new materials. However, the question always arises here. Why do we need them? What do they bring to the table? And as I already mentioned, first of all, this was metallic conductivity. But it has been predicted that surface termination can open band gap and make actually also semiconducting materials here. Exciting magnetic properties, 2D magnetism, including ferromagnetism, giant Zibby coefficient. So it means thermoelectric materials, Dirac fermions, cones in the band structure like in graphene, tunable superconductivity, ultra low work function, many other properties have been predicted computationally. Some of them, for example, superconductivity in niobium carbide, MXene has already been demonstrated experimentally by Dmitry Talapin from University of Chicago in a paper published in Science last summer. Some other properties, like for example, ferromagnetism, tunable ferromagnetism in MXenes in 2D state, are still to be demonstrated here. But it's also very important that it's possible to control the properties not only by changing M and X element, but also changing terminations. You will see that, for example, titanium 2C without surface termination will have a high density of states at the Fermi level, and it will decrease with fluorine termination, and actually a band gap can be opened by terminating the surface with oxygen, pulling electrons away. However, those are idealized structures. Very often we have a mix of surface termination. We have defects which affect real properties of those materials, leading to actually very different properties here. Still, what is very important, and I will keep stressing this, we have an extremely large family of materials. We can have 2, 3, 4, 5 layers of transition metal, connected by 1, 2, 3, or 4 layers of X element, carbon, nitrogen, or their mix. And you will hear about oxygen soon as well. And they can have numerous surface termination. Just do the math and you will come up easily with about 100 of simple compositions. And if you add surface termination, and about 10 have been already demonstrated, you will end up with 1,000 possible compositions. But it's possible to mix them, you remember, on M side and X side. So we really have an infinite number of materials. Moreover, it's possible to order M element in plane. So known in plane, I MXene in plane order it MXene make, or H actually atomic column of one M element, for example, scandium and yttrium, leaving moly or tungsten on the surface and get materials with missing atomic layers, with divacancy layers on the surface. Or it's possible to make atomic sandwiches when one element is on the surface, M element, another is in the middle layer. For example, moly on the surface, titanium in the middle. And high entropy multi-elemental MXenes have been demonstrated earlier this year. The first paper was published like about 2 months ago or even less here. And definitely this is not the end. Predictions have been made for producing a variety of materials. We can actually computationally design them and tell in which combination of elements there will be separation into this layered sandwich-like structure, in which case we get partial ordering, in which case we will get random solid solution here. And for example, in this study, already like more than millions compositions were screened here. Let me also mention one more thing here. People talk about graphene, telling, look, this is the thinnest material available. MXenes are at the moment actually the thickest 2D materials available. This material with 5 layers of transition metal, 4 layers of X element, and surface termination will have like 11 atomic layers, but every sheet will be 11 or 9 or 5 or 3 layers of atoms thick here. So we have discrete change in properties. We have all flakes of the same size, single crystals, but they add stiffness, they add stability of conductivity. For example, when you modify the surface, the material with a couple of atomic layers inside, you really don't affect the inner layer. Imagine like a storm on the surface of the ocean, and you dive a few meters under the surface and the water is calm there. You don't even like feel what is happening on the surface. So this is also important and very interesting here. Now, how do we make those materials? We actually start with MAX phases, a family of materials developed by Professor Michel Barzoum at Drexel University, which are layered carbides and nitrides with A element, one of those blue marked here, and M elements are coming from Z group, and you see carbon and nitrogen here. And we chemically etch away these layers of A element, producing those structures, those compositions that I mentioned to you. And after that, these layers are already connected in a weak way by van der Waals bonds, because they acquire oxygen, OH, fluorine, chlorine, other terminations here. We have been using for a long time wet chemical etching, for example, starting with HF. Now we can use mix of lithium fluoride with HCl, sodium fluoride, HCl, and other compositions here. We used also molten salt for producing nitrides, like titanium nitride MXene. But Professor Qin Huang came up with a method to use molten salt eutectics to make also materials with different termination, for example, like a chlorine or bromine on the surface here. And there have been also other developments very recently showing wet chemical chemistry or synthesis from organic solution using chlorine, bromine, iodine, other etchants here. So there are many ways. What is important is that unlike, say, exfoliation, mechanical exfoliation of molybdensulfide or graphene, we have to use etching because there were initially strong chemical bonds between the A element layers and transition metal in the surface. So we need to etch them and replace them here. What is important in these things here? We can make not only small amount of materials for electronics, optics, sensors, monolayers, but we can make large amount of materials, making printable inks, catalysis, and potentially also enough materials for energy storage, battery, supercap application, and hopefully one day for even construction applications here. Why? Because this is wet chemical etching process. You take a ceramic powder, max phase powder, which was produced like a high temperature ceramic by conventional technology. You put it into reactor and you etch it. And currently we have reactors producing up to 100 gram. There are kilogram reactors in industry, but potentially it can be 100 kilogram, 1 ton reactor here. What you end up with? You end up with a powder here. And actually, you can process it into films, into structures, without any additives from aqueous solutions. Here, just add water. So we start with the ceramic materials, we etch it, we get particles that look like exfoliated or thermally expanded graphite or vermiculite clay. Now, this A element that you can see here, a row, for example, of aluminum atoms, are missing, and you may be able to distinguish here on the surface terminating atoms here. And after that, if you intercalate it, or sometimes if you use, for example, lithium in etchant, it's enough just to shake the bottle. You will get a colloidal solution of single or few layer flakes and from this powder, and you can then process it into films. As I mentioned, even without adding any surfactant or binders. And of course, if you have colloidal solution of 2D particles in water, or you can transfer it to organic solvent, polar organic solvents, you can use all the variety of known solution processes technique: printing, 2D printing, 3D printing, inkjet printing, spray coating, spin coating, interfacial assembly to create films, to create 3D structures. You can even pull fibers, again, from just aqueous solution of two-dimensional MXene flakes and produce fiber, which will be 100% MXene, but again, you can mix it with graphene, you can mix it with carbon nanotubes or other material things here, and it will give you conductivity. There have been challenges, and as any new materials, lots of improvement have been needed. For example, initially, because of defects and not very good stoichiometry, oxidation and degradation was reported. Earlier, we reported in ACS Nano this spring that we can make materials with a good stoichiometry, titanium carbide MXene, which will really not change its property in dilute aqueous solution after storage at room temperature. For months, as you see Raman spectra, which virtually don't change compared to fresh titanium 3C2. And even 10 months storage in solution only lead to formation a couple of pinholes, which are circled here in red, because otherwise you would not even be able to find it. Now, I talked a little bit about conductivity, but there are many other useful properties of these materials. Again, combination by itself of metallic conductivity with hydrophilicity, ability to be dispersed in water or polar solvents, provides a very unique combination of properties. Moreover, we can actually make pretty large flakes. This flakes is about 20 microns. We can do much better nowadays even, and it doesn't break. You will never find publication, for example, molybdensulfide or oxide flakes produced by solution processing of that size, because mechanical properties. MXenes have much higher mechanical properties than other solution processed materials, actually stronger than graphene oxide or reduced graphene oxide. Only pure boron nitride or graphene separated from single crystals will outperform them here. They also have a variety of plasmonic colors that you could see on my first slides here. And again, tunable properties by changing MX, number of layers, ordering of elements in the layers, and surface termination. And this is what gives a lot of properties. But keep in mind, those are still single crystal layer particles. They have ordered structure. You can see electron diffraction from a single flake. And you may remember I stressed importance of having more than a single layer. This flake crystal is suspended in air, and it does not collapse. It is not as flimsy as, for example, a monolayer material like a graphene would be. Few atomic layers make these elements much more rigid here. So we do have materials which properties of which can be tuned by changing their terminations, changing number of transition element layers, or ordering of the layers things here. As a result, you will end up with the say variety of plasmonic colors in these materials, changes in the band structure, changes in work function. For example, from ultra low in OH termination materials going down to 2 electron volts to 6 or even 8 electron volts with terminations by oxygen on the surface here when extra electron atom. Moreover, we can mix those elements, making solid solution, as I mentioned, X sides and M side, and tune properties finely, getting high mechanical strength, getting plasmon resonance, covering actually the entire visible and much of the infrared range here. And let me give you just one example. I don't have much time going in details here. Let's take 3 different examples from this family of materials. Titanium 3C2 will have transfer surface plasmon at about 780 nanometers. As a result, it will be green in solution, but it will be like a purple-like color in reflection, a complementing color. If we change and move to titanium 2C, we will shift the plasmon resonance lower, and we will get it about 550 nanometer. As a result, it will become green in reflection, but purple, reddish in transmission. And in V2C, the plasmon resonance will move even lower. And those of you who work in nanotechnology field, or at least read popular story about nanotechnology, have certainly read about the Lycurgus cup from the 4th century, which by adding gold and silver particles would be made red in transmission, but green in reflection. Compared to titanium 2C, we have abundant elements, titanium and carbon, no gold, no silver, and we get a similar plasmonic combination of properties here. And this is just one of the applications that allows use in surface-enhanced Raman spectroscopy and other devices here. There are many, many different applications for MXene being explored by the community. Several of them are already in the process of being commercialized here, ranging from energy storage to communication antennas, electronics, smart textiles, medicine sensors, and many others here. I'll give just a couple of examples because I don't have time to go into lots of details today here. But if you talk about optoelectronic applications, you know that any materials in a very, very thin film will become transparent pretty much. Titanium 3C2 is not an exception. You just have seen a colloidal solution of particles. And if you make a thin transparent film, it can be used in, for example, organic OLEDs, light emitting diodes, to replace indium tin oxide and pretty much provide the same performance as ITO. But unlike ITO, making these OLEDs truly like a flexible and not cracking when the devices are flexed, bent, folded here. It can be used again instead of gold in current collectors for printing here. It's possible to make aerogels and hydrogels, and this is a stretchable hydrogel which can be used for haptic controls for strain sensing, but also in actuators, also electrochemical and optical actuators for a variety of soft robotic and sensing applications here. Moreover, this variety of properties led Hussam al-Sharif from CAUS call creation of a field of Maxitronics, which are MXene-enabled electronic and photonic devices because of this variety of compositions leading to properties, controlled optical, resport, charge transfer, band structure, work function, and possibility of developing entire electronic, magnetic, plasmonic, spintronic systems using MXenes. And this is a quite exciting future, but we still have a very long way to go, of course, to realize fully MXene devices. And again, I'm referring you to what I stated in the beginning, that the strength of 2D materials is really in their ability to be combined with other 2D or lower dimensional nanostructures here, or code large 3D structures here. Let me give you a couple of more examples from our research. For example, MXenes have been very efficient materials for electromagnetic interference shielding. Traditionally, it was considered that metallic conductivity is really the key for shielding electromagnetic field and protecting our electronic devices from noise, from being read by adversaries. And MXene shows that it can actually outperform copper, gold, other metals with conductivity still a couple of orders of magnitude higher here. It really opened a new field of science for EMI shielding, or in general electromagnetic field interactions with 2D materials here. And similarly, it is great for antennas communication. We can make antennas with radiation efficiency the same as copper, but an order of magnitude thinner or lighter for 5G, 6G, terahertz communication here. In my group, we work a lot on energy storage. Electrochemical capacitors, devices which are akin to batteries, but can store energy and give it much faster. Harvest energy from fast processes. But double layer capacitance made of carbons could store much less energy compared to batteries. So they would discharge much faster. The goal is to move materials towards the area where Elon Musk promised us we are going to be getting to charging within 5 to 10 minutes a Tesla car battery or any other electric car batteries here. So what do we need for this? We need materials which provide high energy and which also provide high power at the same time here. What does it mean basically, charging a battery quickly? It simply means running a very high current through the battery. If you consider oxide materials used today, those are fairly poor electronic conductors. So if you run a high current through a resistor, you just heat it up, leading catastrophic consequences. What is interesting in MXenes, we already talked today more than once about their high electronic conductivity, but there are also galleries between two-dimensional layers where ions with or without solvent can also move quickly. And there is a transition metal on the surface capable of redox behavior. And it can be titanium, moly, vanadium, niobium, many elements that can change their oxidation state significantly here. So ionic conductivity, electronic conductivity, reversible redox. This is a combination properties needed for energy storage, whether we are talking about supercapacitor or pseudocapacitors, storing energy on the surface, batteries of any kinds here. And there is no solid state diffusion involved because those are two-dimensional materials with nanometer thin or thinner layers here. So many applications emerge in the energy storage, covering pretty much almost all kinds of batteries, lithium ion, sodium ion, potassium ion, aluminum ion, lithium sulfur, sodium sulfur, and capacitors, pseudocapacitors here, which actually show extremely high performance and the potential also for AC-DC conversion, line filter application, because the charging rate can go not 2 minutes, but actually to nanoseconds if very thin films of MXenes are used. But remember, we can also make fibers. We can embed those materials into textiles, into wearable devices here. And of course, there are many other potential applications for those materials here. We can talk about gas sensors. The same metallic conductivity to take care, and again, it becomes different compared from other materials. Conventionally, gas sensors are semiconducting sensors, where conductivity changes as gases are adsorbed on the surface. They usually require heating up to somewhat elevated temperature, 100, 200 degrees C, to make them working here because of poor conductivity. In case of MXene, changes in conductivity are caused by adsorption on the surface or by intercalation of molecules between MXene sheets. As a result, there is extremely high sensitivity, and this work was published on the cover of ACS Nano a couple of years ago. And also there is low noise because of metallic conductivity of MXene. So again, just like in case of electromagnetic shielding or antennas, they can really be a game changer in the field, bringing new principles and new opportunities to the field here. And one of the most recent fields of research is biomedical work, application of MXenes in medicine here. It may not look like intuitive application for this type of materials things here, but what is important, titanium, tantalum, many other transition metal carbides are biocompatible, non-toxic. And you remember I mentioned, for example, 780 nanometer transverse surface plasmon in titanium 3C2. In many other materials, they move to infrared, near infrared range. So it's possible to use red light. It's possible to use infrared lasers to hit them. And they have been shown to be among the most efficient light to heat conversion materials here, destroying tumors and they can be used in photothermal therapy. Moreover, it's possible to also intercalate them with drug molecules and simultaneously deliver drugs which also be released upon hitting, killing remaining cancer cells. There is a lot of research, there are already review articles on this, but definitely it's not limited by that. Our colleagues at the University of Pennsylvania, Flavia Panetta and her group showed that it's possible to make implantable electrodes for brain studies. It's possible to make also MXene electrodes for electromyography, cardiography, but other studies again replacing platinum, gold, silver, other metals currently used, and interestingly producing better result because of a better match of impedance between tissue and MXene compared to metals here. They can also be used in ophthalmology, and other applications are emerging here. In my group, we work on developing a wearable kidney, and a company, Nephria Bio, was launched in the US to commercialize this technology early this year. And I'm going just to very briefly mention another property that I stated in the beginning for 2D materials in general, but really did not discuss much for MXenes. 2D materials naturally have high surface area, so they can adsorb molecules. Just like in a gas sensor, we use adsorption to adsorb gas molecules and measure changes in conductivity for sensing purposes. In a battery and supercapacitors, ions are intercalated between the layers. But it also appears that MXenes, particularly titanium 3C2, and this is so far the most studied MXene, can very effectively adsorb urea molecules. And actually, what has been limiting development of wearable kidneys? There is no good sorbent for urea. Activated porous carbon, which are excellent sorbent for majority of biomolecules, are very poor sorbent for urea. And with availability of MXenes, it may become possible to free millions of people suffering from acute kidney disease from a dialysis machine. And this problem has actually been further complicated by the pandemic, COVID pandemic, which both make it dangerous bringing patients to hospitals or dialysis facilities for treatment, but also many people who suffered from severe COVID cases have complications or kidney and develop kidney disease as a result of this. It has been 30 to 40% of patients in New York with severe COVID last year who needed after that dialysis after hospital treatment here. So the problem is very important, and we are very hopeful that MXenes, because of their lack of cytotoxicity, biocompatibility, hemocompatibility, and ability to absorb urea and uremic toxins, will be helpful in these applications. Of course, I could not cover all the applications and properties of MXenes in this relatively short introductory talk here. This plot summarizes some of the applications known. New applications emerge almost every week because every day several papers on MXenes are published here. I talk today a little bit about electromagnetic applications, shielding for especially wearable electronics were much thinner compared to metal foils. Shielding layers are needed here. Stealth, also infrared stealth. Communication, also moving beyond 5G to 6G and terahertz communication ranges here. I talked about biomedical application, dialysis, biosensing, electrochemical sensing, which is also important, cancer treatment, medical electrodes. Sensors of other kinds, gas, strain, moisture, electrochemical sensors. Optical applications, recall all this variety of colors, so it simply means different optical and plasmonic properties, with application in transparent electrodes, lasers, actually femtosecond and random lasers, plasmonic surface enhanced Raman spectroscopy substrates, again replacing gold or silver noble metals, photonics and electrochromics. MXene, by just applying 1 volt potential to an electrolyte infiltrated MXene film, it's possible to shift the plasma resonance peak by about 150 nanometers. So very significantly change the color of these materials, similar to oxides, but because of conductivity, we don't require transparent oxide backing here. Many electronic applications that allow people to talk about Maxitronics today. Catalysis. I didn't have time to talk about it, but again, hydrogen evolution reaction, light to heat photocatalysis, electrocatalysis, chemical catalysis. There are many transition metals known to be excellent catalysts that can be in MXene structure here. Zirconium, moly, niobium, tungsten, and other things here. And MXenes can be incorporated in a variety of matrices, metals, ceramics, and polymers here. Working with Dmitry Talapin from University of Chicago, we showed that it's possible to add titanium-32 to light alloys, almost doubling strengths and Young's modulus without loss in ductility. And of course, they can also add conductivity to ceramics or polymers. Also, of course, adding other properties, mechanical, EMI shielding, and so on and so forth here. And of course, almost any kind of energy storage devices. We actually discovered MXenes working on a Department of Energy funded projects on lithium-ion batteries. So not surprising, much of the research in MXenes was done in the energy storage field. And you can talk about harvesting, triboelectric nanogenerators. Many of you have probably heard a wonderful lecture by Zhonglin Wang in this seminar series here. But what is important? About half of the work done was done on a single MXene titanium-32. Of about 30 stoichiometric compositions, couple of dozen solid solution already experimentally made, and as you have heard, at least 1,000 of stoichiometric composition and unlimited number virtually of solid solution available. So there is so much room for exploration of other MXenes. Many of those applications were first initiated just a couple of years ago. And as I mentioned, several of them just emerged this year, a couple of months ago. Number of type of MXenes, for example, high entropy alloys were reported just about a month and a half or two ago. There is plenty of room for discovery. But what is important, we're also working with a large number of companies. And I know there are quite a few companies already in China offering, selling, producing MXenes to move it from basic science, from research to industrial use. And Terence Barkan, who created the MXene Association, also, or Graphene Association, sorry, also launched a MXene Association earlier this year. This was the introduction in April, on the 19th of April. And the goal is to bring together manufacturers and users of MXene to build the industry base here. So you're welcome to join if you are working in industry, or also universities can become members by going to this website here. And of course, I talked to you today about potential of MXene, successes, success stories, first breakthroughs. There are many, many different challenges. For example, it took quite a while for people to learn how to make graphene, moly disulfide, boron nitride, to grow at the wafer scale by physical chemical vapor deposition techniques. The efforts are ongoing for MXene work by Wen-Tsai Reng, Huimin Chen at the Institute of Metal Research in China, led to very thin crystals, couple of nanometers of moly, carbide, and others on copper, but it's still not a single layer. They actually reported last year another family of two-dimensional nitride and synthesis of moly silicon nitride by chemical vapor deposition things here. So beyond MXene, there are other 2D carbides and nitride structures, many of which have been predicted computationally, not made yet here. And at the third International Conference on MXene in Ningbo, organized by Professor Qin Huang, here the community, scientists working in the field, formulated a large number of challenges that are outstanding. And all participants of the third International Conference on MXene voted for them, ranking them as in priority. I know this list is almost impossible to read, but we published it recently in this editorial in ACS Nano, which accompanied a virtual issue on MXene. And the list of challenges is included in this editorial. So if you want to identify quickly problems to work on, if you are planning to jump into the field and start discovering new materials, new properties, and new applications, this is your excellent guide to the field here. And we see that, of course, improving synthesis method, assembly MXenes with other materials, achieving uniform termination, better control of chemistry of the materials and structure, studying properties of unterminated MXenes which will behave as electrolytes, incorporating them into a variety of flexible wearable technologies here. And of course, demonstrating exciting physical properties, many of which have been predicted, but have not practically realized yet, are the next frontiers in the field here. And it's probably about time for me to finish my presentation. Also, I referred you to this Science article in the beginning as a convenient and very recent overview, even though a couple of important discoveries have been made afterwards here. But also next week, we will be teaching a course on synthesis, characterization, electrochemistry of MXene, a whole week course from 7 a.m. to 12 p.m. Eastern Standard Time. So it is late night, late evening in Asia, or very early morning for people on the US West Coast, very convenient for Europeans and US East Coast people. And it's not too late to register for it, and you will learn everything we know about MXene from my research group here. And this is the very last slide in my presentation. Of course, the work was done by many different people here. There are more than 1,000 organizations in the world that have already published paper on MXenes. There are thousands of patents in Google Scholar here. And just in our group, we collaborate with more than 20 different institutions around the world. I listed here just a few collaborators, scientists with whom we have ongoing active collaboration doing exciting research. We have been enjoying funding from many different sources in the US and abroad. And of course, my research group, those are people who make things possible, make all our papers possible, patents, development of MXene. And this was actually our first mass class gathering this summer for a summer party in the backyard of my home, when we enjoyed finally taking masks off since everyone has been vaccinated by now. And we can also have social events in addition to working in the lab. And thank you very much for your attention. Hope you will find this family of material exciting. There is so much more to do in the MXene field, and I encourage all of you to think about how you can contribute your knowledge, your experience, your enthusiasm to exploring this wonderful family of materials. Thank you.
Thank you so much, Yury. Let me take the screen back here.
Let me stop sharing then.
Oh, I got it. Yeah. Terrific. Well, I think everyone who heard that can see that there's an incredible future for these materials and for Yury and his collaborators. One of the things I left out of the introduction is, I think that biography is going to change very dramatically over the next few years. And so we'll look forward to sharing more from Yury and all his successes. And now it's my pleasure to introduce our panel. First, we welcome back Professor Mizo Kim, who's now an assistant professor at the School of Advanced Material Science and Engineering at Sungkyunkwan Kwan University. When she gave her Rising Star ACS Nano ICANN X lecture, she was at the Korea Research Institute of Standards and Science as a senior research scientist, and since then moved to SKKU, and also joined our Rising Star journal board at ACS Nano. Her research interests cover analytical modeling, design, and experimental characterization of piezoelectric materials and mechanical metamaterials for energy harvesting and sensing. Welcome back. Next, our other panelist is Keely. Dr. Keely is a postdoctoral researcher with Professor Valeria Nicolosi's group at Trinity College Dublin. He received his PhD in chemistry and physics of polymers from Fudan University. And during that time, he also worked as a joint PhD student at the Drexel Nanomaterials Institute with Professor Yury Gogotsi. He's won the Horizon Prize from the Royal Society of Chemistry, the Kwang-ha Award from Kwang-ha Education Foundation, and the Exchange Program Scholarship for doctoral students from Fudan University. His research focuses on the synthesis of nanomaterials for electrochemical energy applications. And our ex-challenger this week is Yiran Yang, who's a PhD candidate in prior speaker, Professor Wei Gao's group in the Department of Medical Engineering at Caltech. She's won the Baxter Young Investigator Award and the CSAC Scholarship, as well as the Forbes 30 Under 30 in Science this year. So welcome to all of you, and let's have you turn on your cameras. Looks like everybody's on. And as tradition, we'll start with Yiran Yang and give you a chance to ask Professor Gogotsi some probing questions.
Thank you, Professor Weiss, for the great introduction, and thank you, Professor Gogotsi, for the stunning and inspiring talk. MXene is such a wonder of materials for so many applications, and I'm sure this field will keep growing exponentially and breaking the limits of 2D materials in the future. So I have a few. I have a question on the process of developing new MXenes. As you introduced in your talk, the tunability offers the versatility of the material. So is the process of designing and developing new MXene mostly guided by some theoretical or computational simulation of the properties? And I actually did see that you mentioned in the new challenges of this field include the providing more reliable theoretical simulation or computation of the property. So I'm kind of like wondering how much is there a mismatch between the expected behavior versus the actual behavior for the designed MXene structure. In addition, is there any possibility, or what is your thought on machine learning in the application for the designing process? Thank you.
Well, this is an excellent question. And also, it clearly shows that I did not speak about modeling and simulation of MXenes enough here. Simulation of properties, prediction of MXenes is extremely important. You can very easily imagine, if you have like thousands of possible compositions, it's impossible to make each of those and study all the properties to determine what's good. So actually, MXenes are among the fields where modeling has really been guiding much of the development. For example, we selected chromium-containing MXene for studying of magnetic properties, which actually also I didn't talk about today, based on the simulation. When we published our first paper in 2011, for about a year, there was not a single other experimental study published. But computational scientists around the world jumped on the opportunity and started to predict compositions and their properties. And after that, of course, explosive growth at certain point started experimentally here. But initially, there were very simplified simulation, non-terminated MXenes, simplistic approaches. Then it went to like a next generation, accounting for surface termination. Then it went to a next level, accounting for defects, for complex and variable surface termination and those properties, with, of course, accuracy of predictions increases. Still, many properties like 2D ferromagnetism, topological insulators, and a number of others are to be experimentally verified and to show whether they're right or wrong here. Working with Professor Vivek Shenoy and his group from the University of Pennsylvania, we actually published a paper on use of machine learning for development of MXene. However, what is needed here? We need a much wider base in properties, because machine learning is good when you can teach the machine, when you can input properties here. But I believe exactly in that field, computational material science, machine learning, and artificial intelligence will play enormous role in helping us to predict and design a material here. Let me also go back to the very beginning of your question, Yoran. When we discover new materials, new MXenes, we also depend on max phases, because we currently use max phases precursors here. We may learn to make it by different ways, but typically those are either max phases or other similar layered carbide, like for example, aluminum carbide layers, zirconium carbide layers, where we'll remove entire layers. So we need to predict not just MXenes, we need to predict their precursors. And what is interesting, now the community is actually designing and making new max phases with the goal exactly to produce MXene for them here as intermediate things here. So yes, basically, if you are doing DFT, MD simulations, work on machine learning and artificial intelligence for material discovery, that's MXenes are your baby. It's something, your toy to play with.
Thank you so much. If it has any if it has any anti-fouling properties, or how the performance would it be in real like biofluids where there's so many so many proteins or even other matrix in the fluid. Thank you.
This is actually also an excellent question. And actually, this is a problem we are working on right now. You should be able to read in Science Translation Medicine a nice article about medical electrode application of MXenes shortly. And there are good things and bad things about MXenes here. First of all, let me also tell, in most cases, when I talk about MXene, I still talk about titanium 3C2 as the most studied one and most widely used one in applications here. It's biocompatible, and actually it has anti-fouling properties. We initially worked with colleagues from Qatar Energy Environmental Research Institute on application of MXenes in water filtration, desalination. And this is where we observed those anti-fouling properties and antibacterial. And actually very recently, Aselia Yilmazer and Lucia Dalogo showed that also antiviral properties, even against some strains of COVID, basically coronaviruses, are available. So they're anti-fouling, they're biocompatible. Now, I praised hydrophilicity of MXene many times, but also it has its challenges, because if you assemble in film, it can potentially again absorb water and ions and swell. You can use it in sensing, but if you have an electrode which you implant and we need to work inside the body for extended period of time, you don't want to change its properties with time. So we need to find better ways to ensure long-term stability. And we're also starting to understand how MXenes, and not only titanium 3C2, but a number of others used for medical imaging and other applications, behave in the body, how they interact with proteins and amino acids. I just spent an hour yesterday with one of my PhD students in the lab looking at amino acids at MXene surfaces, trying to detect them by Raman spectroscopy and source unsuccessfully, by the way. And not every experiment we do leads to successes. Again, don't get discouraged here. But this is something very important. We still know not enough to ensure safe use of MXene in biomedical applications and improving stability, ensuring biocompatibility and no long-term negative effects, and simply understanding at the fundamental level interaction of MXene with a variety of biomolecules is extremely important for its applications. So thank you for this question.
Thank you very much.
Very good. I think what we'll do is move around the panel, and then we'll come back again for more Yuran when you're ready. But let's give the floor over to Professor Mizo Kim next for questions for Yury.
Okay, Yury, thank you so much for your always wonderful talk. So I have two academic questions regarding the MXenes and one personal question you might want to answer. So the first one
I'll do my best.
Yeah, I've been always wondering about the birth of MXenes. Actually, it's amazing that you're a pioneer of some new field, right? So I was wondering how you discovered the material, like you planned and you calculated the materials and you predicted the materials invention first and then experimentally realized that, or you kind of discovered like by accident?
That's pretty long story.
Okay.
And if you want to read details, I would refer you to an introduction to our book on MXenes that you could see on the cover slide. Together with Professor Michel Barzoum and Michael Naguib, we described this discovery. As usually, of course, it was not a single person work. It was a great team effort And also several of my postdoc and students were involved in characterization of these materials. And our colleagues from Sweden provided the first high-resolution TM images. But this was a combination of basically serendipity, luck, coincidence. We were actually working on a project to incorporate lithium into titanium silicon carbide MXphase. And lithium refused to go in, even though our DFT prediction suggested that the energy barrier is not very high. We were able to accomplish it a few years later, but at that time it didn't. So we decided to use selective etching technique, which we have been using for making carbide-derived carbons, many other materials, to make room in the layers of MXphase to allow lithium insertion here. And Michael Nagib, who was a PhD student at the time, working with Michel Barzou, myself, tried many different MXphases, many different etchants, until he found that HF etched MXphase. And this was again a surprise. He initially checked many phases. Titanium silicon carbide, my other PhD student was able to etch just like 6 years later. He found that titanium to aluminum C carbide reacted very quickly with HF solution. But when he did analysis after that, he found not titanium 2C, he found titanium 3C2. And my postdoc, who is now a professor as well, who did TM analysis, he did first TM analysis and told, you got graphene, because he saw two-dimensional sheets of material things here. After that, we realized that what left was titanium 3C2, which was an impurity in titanium 2 aluminum C carbide, as titanium 2 aluminum C MXphase. And after that, Michael repeated experiment on titanium 3 aluminum C2 carbide, and then synthesis of titanium 3C2 was confirmed, and we were able to put a paper together after proper characterization of material by several techniques here. So again, sometimes lack of success in one project leads you or forces you to move in a different direction, and may lead to a discovery which I would say definitely appeared to be, at least scientifically, much more important compared to what we initially tried to accomplish here. But again, read the entire story in the book. It's again a good lesson for people, particularly younger scientists who feel sometimes lost. I do something, it doesn't work. I see something that I was not supposed to basically to find and not what I was planning to do. Should I just ignore it, walk by this? Should I explore and see what happened and what I found here? So again, keep your eyes open. Anything unusual is interesting, and whenever you fail to do something, it's not a failure. This is research. If you do something that's easily done, predictable, will certainly be done, it's not really cutting-edge science.
Oh, thank you so much. What a story. I love that encouraging part and inspiring part. So I have to work on my current project to lead to something else. Yes, I will.
Always possible.
Yeah. So my second question is, what do you think is the dominant, more dominant hurdle to the commercialization of MXenes? So, for example, like material property improvements, like a conductivity, or the like large scale production, the mass production.
I think it's really production synthesis, and it's not uncommon. Moreover, traditionally, it used to be 15 to 25 years before new materials discovered would go into practical applications and production here. And even though I stress that MXenes are among actually very few nanomaterials that can be produced in already significant quantities, there are really a handful, like a graphene, moly disulfide, tungsten disulfide, boron nitride, of 2D materials that are available in more than milligrams or gram quantities here. There's still produced in quantities which are not sufficient for very large scale applications. And you need to look for application where small amount of materials required. For example, these thin transparent electrodes, source substrate, sensors, where amount of material used are relatively minuscule. And you know, like from a 50-gram batch of material we can make routinely in the lab, you can cover enormous area with few layer film of MXene. So you can make already today enough material for those applications here. And then hopefully others will come. Still at the moment, those are small company producing MXenes. Murata, which is a very large Fortune 1000 company, is working actively on developing MXene products. I cannot expand into exactly which ones, but on commercialization. Millipore Sigma, which is the largest supplier of chemicals for research, licensed technology from Drexel, and already published brochures and will make material MXenes available starting earlier 2022. COVID delayed the release. They already offer max phases as precursors here. And as I mentioned, there are a number of smaller companies producing on licensing from Drexel, like 2D semiconductors, but also many companies in China offering MXene max phases here. So I think just for us, like for other nanomaterials, this is where quantity will transition into quality and real products with time. But yes, it takes time, like for any other new material.
Yeah, thank you so much. So I have one more kind of a personal question. So I sense that you got quite inspired from your dad, who is also a really renowned scientist, I guess. So would you want to tell any like one of the inspirations you got from your dad, like so that you can get inspired from our parents, or we can become parents like that?
Well, I think we all have in our life people who inspired us, helped us. My father is a scientist. He has been working until very recently, and actually I saw a week ago that a paper that he co-authored was published in Ceramics International. He worked on mechanical properties, mechanical behavior on ceramics. He will be 91 on the 2nd of August. He lives in Ukraine. I'm originally from Kyiv, from Ukraine, and he has been working until very recently. And we know many examples of scientists like John Goodenough just celebrated his 99th birthday, and he is still staying active here. So he supported my interest in my research. And he is a person interested in mechanics. He was trying to inspire me to work on mechanics and physics and engineering. And I loved chemistry. So he took me to a chemistry club when I was a kid and helped me as much as he could to basically do what I wanted to do. So on one hand, I always observed a scientist doing research. I was excited going visiting his laboratory. On the other hand, I found in science something I really loved, that intuitively I felt this was mine, something I could easily understand, grasp. And particularly, I like also high temperature and explosions. So this led me to metallurgy and material science, which is basically was and still is high temperature chemistry here. And I had a couple of other wonderful people. Our chemistry club instructor, Sergei Mikhailovsky, his latest job was professor at University of Brighton in England. And we even collaborated, published a few papers. He is doing consulting. He retired, but he's doing consulting. He has a small consulting company now. So again, you know, like we all need examples to follow, and we find people who serve to us as role models. Just basically talk to those people, try to learn from them. And it can be your parent or your relative. It can be your teacher. It can be a university professor, or it can be someone like John Goodenough. I consider him to be one of my role models. This longevity, this ability to do excellent basic science and transfer it to practical applications here. Its ability to continue making discovery after basically retiring from his university in England and moving to the US, to Texas, Austin, I think, and you know, like I was blessed to have a chance to work on a proposal with John, and I really admire people like him, like Stan Whittingham, as a prominent scientist in the field here. So again, follow your dream, look at other people, and try to be even better than they are.
Oh, thank you so much. It's lovely. It's a lovely story. So yeah, really, Professor Goodenough and your dad are such an inspiration. Thank you so much.
Maybe I can add an epilogue to that, and that is I've had a chance to get to know Yury's children.
Oh.
And both Natalie and Pavel are successful engineers and just as warm and funny and bright as you might expect from seeing Yury, and that their entire family is quite a close team. Luckily, we have both his children in Southern California, so we get to see him and them fairly frequently. And so I think you're right on target to say, how both do you get inspired, but how do you inspire your children to be successful and happy?
Thank you, Paul. Both my children decided to go to industry.
So I get to embarrass them instead of you.
Yeah, but they do creative work in industry, so you don't necessarily need to be in academia to be creative and do something wonderful and useful.
Very good. Let's give Dr. Keeley a chance to ask questions as well here.
Okay. Thank you so much for introduction, and thank you, Yury, for this amazing talk. I have several questions, in fact, and the first one is about the future researches of MXene. Since I'm working on energy storage, so most of people are also working on this field. So I'm wondering if you could give some suggestions or comments on the future researches of MXene on energy storage, or how can we make new breakthroughs in this area? Thank you.
Well, Kim, you are a MXene expert yourself, so you probably don't need much of my advice here. But let me just tell in general for everyone working, and also not only in the energy field. When we look for applications, we always build our approach on basic science and understanding of material in its properties and the needs. Not just trial and error. Okay, everyone works on lithium-ion battery. Let's take every possible MXene, throw it in, and hopefully one of them magically will produce a great electrodes or a current collector or become a good conductive additive here. What we need to do is two things. One, look at the problem. Say where the need is. What can be done, what is useful, what is needed. And you can identify a few needs in energy storage. For example, we need batteries going beyond lithium. And in this case, say metal sulfur batteries are potentially high energy and also lower cost solution. What do we need? We need materials, say, able to adsorb polysulfides. We need materials with very high conductivity compensating for poor conductivity of sulfur. We need materials where lithium will grow without forming dendrites. And actually, MXenes can provide all those properties, and we studied them and we know its promising application. We look where very high conductivity is needed. It's a high power devices, basically battery, supercapacitor, hybrid type of devices. I talked about ability to print MXene, make thin transparent devices, flexible devices, printable devices. So it means that again, For printable electronics, we need printable batteries. We also need energy harvesting solutions from tanks, triboelectric nanogenerators to potentially also antennas for wireless harvesting things here, or eventually combining MXene's electrode with piezoelectric materials. Mr. Kim works on one of very interesting future application things here. So basically, my suggestion to everyone who wants to explore new field, explore new materials, look at the material properties, think where those properties can be useful, and compare them to needs in a certain field, and see where you find a match. And many applications can emerge. For example, Professor Bin Shu from BUCT, Beijing University of Chemical Technology, and his group did some beautiful work using MXene as a conducting binder and also active component of electrodes, removing from electrodes polymer and binding them and making current collector free and binder free electrodes by adding MXenes. It gives flexibility, it removes metal current collector, it changes the process here. So those type of smart approach based on understanding, we have large 2D flakes, we have high electronic conductivity. This is maybe an application which is not necessarily intuitive, but which can make a difference here. So this is approach here, science. And also going back to Yang's question initially here, if you can do predictions, look at the guidance maybe already published by theoreticians, models available, predicted properties, and say, okay, for example, which MXene will be able to bind polysulfide stronger and go with that one without, like, again, testing experimentally dozens of different materials here. Hope this answered your question.
Yeah. Thank you so much, Yury.
I'm not trying to give a specific prediction, use this MXene for this particular application here, but I think a generic methodology is much more important.
Yeah. And my second question is not about science, but it's about career. Since we are now facing some difficulties on transferring our roles from postdocs to assistant professors. So do you have any suggestions for the young scholars how to become a good individual researcher?
I think becoming a good researcher and getting a faculty job, two somewhat different things, but I know this is a challenge many people face. Sorry, I've been speaking too much. And there are a few things. First, I think it's much more important to become a good researcher, because if you're a good researcher, you will find many opportunities. Say, my daughter got a PhD degree from UPenn, and she went to work to one of the most prominent industry labs to do research there, because she was interested in industrial research. Ms. Kim, who is on this panel, worked first in a research institute and then transitioned to a faculty position. And I think there are different paths possible. You can do research in national labs, you can do research in industrial environment, you can do research at universities. And if you're a really good researcher, if you demonstrate by your efforts, by your level of knowledge and understanding that you're really good, you will be able to select where to go. You will find a position. Also, we all know COVID put a number of restrictions on ability of people to move around. There are geopolitical changes which also affect everyone. But this is also a big world. There are more positions open in some countries, in some areas which experience growth. So look also broader. Last year, several of my postdoc students went to different countries, went to Europe, went to Singapore, went to China, went to work in other countries, finding positions all over the world, not only in the United States here. So I think also, if you broader geography of your search, you will find that there are opportunities in some places which may not be available in another place here. So be open-minded, and again, think what your personal goals in life. And if you are good in your field and you pursue your goal, just never give up. Go pursue your goal, and I'm sure you will succeed.
Thank you, Yury. Thank you so much.
I think that's a wonderful note to conclude for today. So thank you to all our panelists and to Professor Yury Gogotsi for another wonderful talk. I learn more every time I hear you speak, and I go out of my way to hear you speak. So thank you for coming back to ICANX today. And we have more to come. Oh, sorry. This is where we would normally, walk across the room and I would present you with a certificate. But in fact, we'll get to see each other in person for the first time in a year and a half next month at the ACS meeting, where Yury will be winning the ACS award in materials. And so we're looking forward to that symposium and to the associated celebrations in Atlanta, Georgia. And then coming up next week, we'll have Liangyi Chen hosted by Lan Yang. So please do tune in for next week's talk. And we'll have a tremendous program coming up throughout August. Thank you once again, all. Thank you, panelists, and to our organizer, Alice Yang, who puts these on each week. Thanks, everybody.